In this video, we're going to talk about limits at infinity and horizontal asymptotes. So you probably have a good idea what a horizontal asymptote is. That's a horizontal line that a graph approaches and follows. We're actually going to be a little bit more precise and demanding than that. We're going to say that, basically what we want is, here's what we want in a horizontal asymptote. We want a horizontal line, and the graph can be made as close as we want, or anybody else might want. In other words, arbitrarily close to that horizontal line by just going out far enough, either on the positive x-axis or on the negative x-axis. So in this definition, think of L as the y-coordinate of that horizontal line. So y equals L, that's going to be our horizontal asymptote. So let f be a function and let L be a real number. If for every positive number epsilon, there is a positive number b, so that the distance between f of x and L is less than epsilon. Another way to think of that is that f of x can be made close to L, and that's a vertical distance. Now, what do we mean by close to L? Well, smaller than epsilon for any positive epsilon. So arbitrarily close. The vertical distance between the graph of f of x and this horizontal line y equals L can be made arbitrarily close to 0 if for every x bigger than b, b stands for big number, so if x is big enough, this happens. And if this is fulfilled, then we say that the limit of f of x as x approaches infinity is L, and we write it this way. The limit as x tends, I think it's probably a little bit better to say the limit as x tends to infinity. It doesn't really mean anything for x to approach infinity, but sometimes I catch myself saying that. Anyway, the limit as x tends to infinity of f of x equals L. Very loosely speaking, the limit as x tends to infinity of f of x equals L says that as x goes larger and larger without bound, f of x gets very close, arbitrarily close to L. So for instance, what is the limit as x tends to infinity of 1 over x? What happens to 1 over x as x gets really large? Alright, so maybe we can let's make a table. So I've got x's here and 1 over x here, and let's pick x larger and larger. Alright, so if x is 1, then 1 over x is 1. If x is 10, then 1 over x is 10, which is 0.1. If x is 100, then 1 over x is 0.01. And if x is 1,000, then 1 over x is 0.001. And so you see that as x grows larger without bound, that's really what is going on when we say that x tends to infinity. That this 1 over x gets closer to 0. And in fact, we can make this as close to 0 as we want by picking x big enough. So that's 0. Alright. Now we're going to talk about the limit as x tends to negative infinity. So let x be a function and let L be a real number. If for every positive number epsilon there is a negative number n standing for very negative number. So number far out on the negative x-axis, far to the left on the negative x-axis. The vertical distance between the graph of f of x and this horizontal line y equals L can be made smaller than epsilon, for every x to the left of n. Then we say that the limit of f as x tends to infinity, or rather tends to negative infinity, is L, and we write the limit as x tends to negative infinity of f of x equals L. So for instance, what is the limit as x tends to negative infinity of 1 over x? Well, we can play the same game we did last time. Now what we're interested in is a set of x's that are negative and getting more and more negative. So we're going to get so I chose negative 1, negative 10, negative 100, negative 1,000 just to give you an idea of what I mean. This is going to be negative 0.1, negative 0.01, negative 0.001. Again, as x tends to negative infinity, 1 over x approaches 0. Can be made as close to 0 as anybody might choose. Alright, so what about the limit as x tends to infinity of 1 over x squared? What's going to happen to x squared as x tends to infinity? Well, x squared is going to get big even faster than x did, and so you're dividing 1 by really big numbers. I hope that it makes sense that that's tending to 0. And the same for negative infinity. If x is a very negative number, then x squared is a very large positive number, and so that's also tending to 0. Now what's happening here if the limit as x tends to infinity of 1 over the square root of x? Well, square root of x doesn't grow large as fast as x does, and certainly not as fast as x squared does, but it does still get larger without bound, and so that denominator keeps getting bigger and bigger, and there's no no constraint on how large that denominator can get. So that's also tending to 0. And what about 8 over x? Well, you're still dividing 8 by bigger and bigger numbers, and the result is still tending to 0. So here's a result which will be useful. Let k be any real number, and let r be any positive real number. Then the limit as x tends to infinity of k times x to the r power is 0. So x to any positive power down here in the denominator, and then k can be any real number. As long as it's fixed, we're dividing this fixed real number by values of x that are getting larger and larger, and so that limit is 0. Further, if k over x to the r is defined for negative values of x, then the limit as x tends to negative infinity of k over x to the r is 0. Now, this part about being defined for negative numbers, let me give you an example. If we were looking at 1 over the square root of x and then taking the limit as x tends to negative infinity, well, we would be interested in only negative values of x, and if you put those under the square root, you'd be getting irrational, non-real numbers, and we're not really interested in the calculus of non-real numbers at this stage. So sometimes this is defined for certain values of r and not for other values of r. So, but if it is defined for negative values, yes. So if this thing is defined for negative values of x, then that limit is 0. All right. So for instance, can you take a look at this and figure out what the limit is? The limit of the quantity 5 over x to the 4th plus 2 over x, the cube root of x, as x tends to infinity. This denominator is getting large, arbitrarily large, large without bound. So is this one. So they're both tending to 0. That limit is 0. How about this one? The limit, I need to make a little bit of correction here. The limit as x tends to infinity of sine of x over x. Now, you may be thinking, we've seen that before. The answer is 1. Almost. What we were looking at before was the limit of sine x over x as x tends to 0. And this is a different matter. So what are we going to do? Well, you may recall that the sine of x is always between 1 and negative 1. So if I divide all 3 parts of this by x, we know that that's tending to 0, that's tending to 0. This gets trapped in between, so by the squeezing theorem, that also tends to 0. So the limit as x tends to infinity of sine x over x is 0.